Hello everyone, I'm back. I'm Bobby Figueroa and this is session number 6. We will be talking about predicate logic, and in this part of the series we will be talking about syntax and semantics. So this is the agenda. We'll be talking about basic terms, what are predicates, and we will be representing predicate logic in terms of symbols, and finally we will be proving if a predicate is true or false. So predicates, or first-order predicate logic statements or sentences, are actually composed of two parts. The first is predicates and the second is quantifiers. So let's talk about the first part, predicates. In English language, predicates are the verb part, or the part that describes the subject. But in logic, it's actually composed of the whole sentence. It's composed of the verb part, or the descriptor, which is outside the parentheses, and inside the parentheses is the subject, which is usually represented by a constant or a variable. So let's look at these examples. In English, Rizal is a man, can be represented by man, quantity, Rizal. As you can see, Rizal here, the subject is inside the parentheses, and the predicate part is man, which is outside the parentheses. And the next one is X is a man, can be represented by man, quantity X, or man of X. X eats Y is represented by eats, quantity X, comma Y, or it can be easily said as eats of X, Y. Next, Juan eats pizza can be represented by eats, quantity Juan, pizza. So as you can see, it's really pretty simple. You just have to put the predicate part outside and the subject part inside. The second part, or the second element of predicate logic statements or sentences, are the quantifiers. The quantifiers indicate quantity. Basically, that's the meaning of it. So it can be all, it can be some, it can be none, or it can also be just one. It also answers the question, how many? There are two types of quantifiers in predicate logic. The first is universal quantifiers, which is represented by this symbol here. This is read as for all x, p of x. So it can be read as for all x, p of x, for each x, p of x, for every x, p of x. The second type is called existential quantifiers. This is symbolized by the reverse E. So it can be read as for at least one x, p of x. There is an x that is a p of x. For some x, p of x. And there exists an x such that p of x. So that's how you can read it. For me, I just conveniently read this as for all x, p of x. And this is for some x, p of x. So let's try translating some sentences that involves predicates and quantifiers. Look at this first example. All UP students are intelligent. First, we try to express or restate this statement in terms of x. First is S of x. X is a UP student. So this is the first thought. S of x means that x is a UP student. The second one is I of x, which represents x is intelligent. So now, if we apply the quantifier, we can first state this as an implication. S of x implies I of x. This means if x is a student or a UP student, then x is intelligent. Now, we put it inside the universal quantifier so that it will mean that for all x, if x is a UP student, then x is intelligent. So this has the same thought when you compare it with this example. So all UP students are intelligent can be represented by, for all x, if x is a UP student, then we know that x is also intelligent. Next, some UP students are intelligent. So for this kind of keyword, we will use the extensional quantifier. So here we have to express this sentence in terms of two thoughts. First is S of x again, where x is a UP student, and I of x again, where x is intelligent. So now we will be using the AND symbol. X is a UP student, and x is intelligent. Now we enclose these with the extensional quantifier. We can read it as, there exists an x where x is a student and x is intelligent. So if you look at it, the thought is the same as some UP students are intelligent, because that means that there exists an x where x is a student, a UP student, and x is also intelligent. The thought is the same. So this is how you translate an English sentence into predicate logic in terms of predicates and quantifiers. And what can you see with this pattern? If you've read the book in terms of the examples, you can generalize two things. First is an implication usually accompanies a universal quantifier. So for all x, p of x is often followed by an implication. For all x, p of x implies q of x. Like in this example, all UP students are intelligent. For all x, if x is a UP student, then x is intelligent. Now, another generalization. Again, this is just a pattern that we can see. I can't say that this is true for everything, but it's a very common pattern. Existential quantifier, which is for some x, p of x, or there is an x that is a p of x, is often followed by a conjunction. So for some x, p of x and q of x. Like in this example, there exists an x, or for some x, where x is a UP student and x is intelligent. So when you translate English sentences into predicate logic, try to observe these two tips. Now let's look at semantics. Semantics is actually the meaning behind the statements, and it's usually associated with the truth value. So now we will talk about how to say if a predicate logic statement or sentence is true or false, or how to prove it. So first, we can prove that a universal quantifier with a predicate is true if we show that for every x in the universe of discourse, the proposition p of x is true. Now, we can say that it's false if we find a counterexample. Like if we say that all dogs are blue, we can say that it's false by just identifying a dog that is not blue, right? But if we want to say that it's true, if we want to prove that it's true, then we have to try to prove it by looking at every single dog in the world and proving that all of these dogs are really blue. So that's how you prove the truth value of a universally quantified predicate. How about an existentially quantified predicate? So how do you say that it's true? It's true when you just find at least one, or just find one instance that satisfies the statement. For example, for some x, and x is a human being, and x is intelligent. So that's equivalent to some human beings are intelligent. So you can say that that is true, you can prove that that is true by just identifying one person, one known person, that is intelligent, right? But how will you prove that the statement is false? You have to look at all human beings who lived since the beginning of time and prove that all of them are not intelligent, right? It's just actually the opposite of this first one. Here, in a universally quantified predicate, you'll have to look at all instances in the universe and prove that the statement is true. But here you have to prove that in terms of all instances of X in the universe, the statement should be false. So I know that it's kind of abstract still, so let's try to give some examples. Let's look at this example. For every real number, x squared is greater than or equal to 0. And this is true. How do we prove that this is true? We know that for any value that you plug into x, to this one, we will know that it will always be greater than or equal to 0. Why? Let's try some examples first. Let's try 2. 2 squared is equal to or greater than 0. 4 is actually greater than 0, so that's correct. How about 0? 0 squared is equal to 0, so this is still true. What about negative 2? Negative 2 squared is also 4, so that's also greater than 0. So now let's try to imagine a number that you can plug into x wherein it will be less than 0. Is there such a number? No, because the only number that will ever be less than 0 is a negative number. And is it possible for us to have a negative number for x squared? No, because anything that you square will be a positive number. So that is the end of my proof. You can also try to draw a graph, and the graph will show in the Cartesian plane that the U-shaped graph of x squared will just touch 0 at one point, but will never be lower than 0. So that's also a good proof if you use a graph. So please review your algebra and your geometry classes in your math classes. It will be very useful for proving. Another one is this. For any real number x squared minus 1 is equal to 0, and this is false. So how do you prove that this is false? We will try to look for a counterexample. And what is a counterexample? We choose 1. When you plug in 1 in this equation, then 1 squared will just be 1. And 1 minus 1 is 0, and 0 is not greater than 0. So this is indeed false. That's the end of your proof. Once you have provided a counterexample, then that's enough as proof. 0 minus 1, actually another example for this is 0. 0 squared is 0, 0 minus 1 is negative 1, and negative 1 is less than 0, so it's also false. Okay. Next example, for some real number, so this is now for an extensionally quantified predicate. For some real number x, 2 over x squared plus 1 is equal to 2/5. Now for this, because this is for some, you just need one example. Just need one example of x wherein this will be satisfied. You don't need to prove everything because it just says 1 or some. Okay? So in our case, we plug in 2, x equal to 2. Let's try to see if it's correct. 2 over 2 squared plus 1 equals 2 over 5. 2 squared is 4, so 2 over 4 plus 1 is equal to 2 over 5. Then this next line would be 2 over 4 plus 1 is 5, right? So 2 over 5 is equal to 2 over 5. So this is true. Because this has satisfied it, and we have provided one example, then this statement is true. Okay, so now let's look at the last example, which is a bit tricky. The last example is for some x, 1 over x squared plus 1 is greater than 1, should be false. How do you prove that? The book has provided a different way to prove it. It tried to look at the opposite and tried to prove that it's true, so that this is false. It's a nice proof, but you can also use this one that I'll be providing. The first statement is, the only way that this will be true, this statement will be true, is if x squared plus 1 will be less than 1 and greater than 0. In other words, this denominator here should be a fraction. Okay? Example, 1 over 1/2 is actually 2, right? And 2 is greater than 1. So that will satisfy this statement. And we want to try to find that first, because we want to say that it's impossible. So let's try to look for its possibility first. Now, if that's the case, then we have to make sure that x squared here is negative. Why? Why should it be negative? Because it's the only way for decreasing this value, which is 1, and making it between 0 and 1. So it should be negative, and it should also be a fraction, like negative 0.5 or negative 1/2, right? So if x squared is negative 0.5, then negative 0.5 plus 1 is positive 0.5 or 1/2. And that will make this expression 2, right? But now the question would be, is there a way wherein x squared can be a negative fraction? Actually, in the previous example, we said that if x is squared, then it's always positive, right? So since it's impossible for this to be negative, x squared to be negative, then we can say that it's impossible for x squared plus 1 to be less than 1. Hence, the statement is false. So now the next example, or the next proof that I'll be showing you, is a graph where this part here is the graph for 1, and this here is the graph for 1 over x squared plus 1. So as you can see, as the value of x decreases, this is the pattern. It also goes down. Peak is 1, which is actually where x is 0. If x is 0, then 1 over 1 is equal to 1, which will still make the statement false. So as you can see, there's no way for this graph to surpass this graph, or to be higher than this graph, which actually proves that this statement is false. So that's the end of the proof for using a graph. And thank you for listening. Some announcements. The initial schedule for your midterms has been moved to October 25 to 2014 to give you more time to prepare. It will be a sit-down exam, so please try to make arrangements with your work, and you have to contact your learning centers or testing centers to be able to take this exam in those locations. Now, if you have a special situation that you need to open with us and you can't really take the exam on this date, please send us an email and we will talk about it. So thank you once again for listening. See you in the next session. Goodbye.